Hello and welcome to the next video lesson on electronic structure. And so what we'll do in this video lesson is we want to know and be able to write the electron configurations of atoms and ions up to atomic number equal 36. And atomic number 36 is krypton, which gets you to the end of period 3. What you'll remember is that at GCSE you do up to atomic number 20, that's calcium, and those positions 20 and 36 are carefully chosen. At GCSE you don't want to bother with transition metals, so you stop just before the transition metals, and at A level you do want to learn about the transition metals and their electronic structures. And so that's why we stop at 36 instead, including the whole of period 3. So as well as that, we want to be aware that for transition metals, the order of filling electrons is different from their order of loss of electrons. But more on that later. So first of all, let's have a look at electron shells. And it might be worthwhile just recapping what you learnt at GCSE, because it will make it clear when we differentiate between GCSE and A-level. It will make the first concept clear. So if we have a nucleus in the middle of an atom, at GCSE we said that we've got electrons in shells, and the first shell is near to the nucleus and the second shell is further away from the nucleus. We represented them as circles, or spheres in fact, around which the electrons travelled. And then we had a look at the third shell as well. So if you remember, let me just label these for you. So we have shell number 1 and number 2 and number 3. We only looked at 3, and you will remember that there was 2 electrons in shell number 1, there were 8 electrons in shell number 2, and in shell number 3 we also had 8 electrons, which we'll do at GCSE level because we only go up to calcium, so that's fine. You'll see at A level that the third shell holds a few more than 8 electrons. So I'm just going to label GCSE, and I also want to introduce a new term for you. That's principal quantum number. Principal quantum number. And the first shell is principal quantum number. Let me write that in green. First shell is principal quantum number 2. Second one is the first shell is principal quantum number 1, second shell is principal quantum number 2, and the third shell is principal quantum number 3. And the other thing that you were aware of is that as the distance from the nucleus increased, the energy level increased. And that's generally true, although at A level we'll find that there's a few little quirks that we want to be aware of. Okay, so let's move on to A level now, because what you will see is that you'll see that this doesn't really describe what an atom's like very well at all. So let's start with the nucleus again, and at A level, just like at GCSE, the first shell is spherical and exists with 2 electrons. And when we look at the second shell, what we need to appreciate is that the second shell consists of 2 subshells. So I've done the first subshell in blue, and I've done the second subshell in green. So that's because what I want to do is I want to label this. This is the first principal quantum number, and this is called an s orbital. And the other blue one is the second principal quantum number, and it's also an s orbital, and as it happens, s orbitals are spherical. Now the other s subshell, the other second subshell, is called the p subshell. All right, so I'm going to write, I'll just switch to green then and write 2p. Okay, so in the second shell or energy level, you now see that it's split into two sublevels. You've got an S and you've got a P sublevel. But that's as far as it goes for the second energy level. When we go to the third energy level, it's actually split into three sublevels. Okay, so I'm going to label these again. So in blue we'll write 3s here. So you see the first one is in blue again, but it's the third energy level, so we're going to call it 3s. And we also have a 3p, which is the middle one here. And now we have a red one as well. Okay, and that's a D. So I'll write this in there. That is 3D. So now you can see that the third energy level is split into three sublevels, 3s, 3p, and 3d, and they all hold different numbers of electrons, which we'll come on to in the near future. Okay, so but we've got another energy level now at A level to consider, the fourth energy level. And we don't need to know the fourth energy level in much detail, but you know, to at least this much detail that we're going to do now. So in the same way, you'll be able to guess by now that the blue sublevel, so the fourth shell is split into 1, 2, 3, 4 sublevels, and the blue one you will be able to work out is going to be the 4s, and then the green one is going to be the 4p, and the red one is going to be the 4d, and the, what colour is that? Brown. Okay, so brown, we're going to call it the 4f. Okay, so just to summarize there, the fourth energy level is split into 4 sublevels, 4s, 4p, 4d, and 4f. Now what I want to do at this stage, because you won't see a diagram like this in a textbook, because it's not quite right. And the thing that there's two ways that it's not quite right. And the first is that I've drawn these sublevels as sort of circular or spherical sublevels. And that's not what it's like at all. The S sublevels are spherical. But P's, D's, and F's are not, certainly not spherical. There are all sorts of different shapes. And I'll show you the shapes of these orbitals or sublevels shortly. But just to illustrate, this slide is just to illustrate the fact that each of these energy levels are split into sublevels, and the sublevels are S, P, D, and F. So that was the first way that this diagram is not quite right. The second way is that in reality we have a bit of an overlap between the highest energy levels of energy level 3, that would be 3D, and the lowest energy levels of 4S. Okay, so what actually happens, and we'll deal with this in more detail, is that the 4S energy level is actually a lower energy than the 3D energy level. So the 4s electrons end up being filled, the 4s subshell rather, end up being filled with electrons before the 3D electrons. So that's that. But you can sort of view this diagram here with all the sublevels. You can view it in terms of distance from the nucleus. Right? Again, it's not really quite right. So it's, if I'm going to write here distance from nucleus, then it's sort of true that 4s is further away from the nucleus than 3d. But at GCSE, you'll remember that it was energy levels. The third energy level would be of a higher energy than the second energy level, and the energy levels increased as you went away from the nucleus. That's generally true, but at A level we come to understand that it's not universally true, because the 4s energy level is actually a lower energy level than the 3d energy level. So now let's consider orbitals. And I've got a slide here for you that lists out the subshells that we've just mentioned, S, P, D and F. And you'll remember that in the first shell, energy level, we have just one subshell, that's the S subshell. In the second energy level, we have both S and P subshells. And in the third energy levels, we have SP and D subshells, and in the fourth energy level we have an SPD and F subshells. Okay, so the subshells are made up of orbitals, and an S subshell has one orbital. All right, so I'm going to write a number 1 in there. An S subshell just has one orbitals, and for any orbital, I'll even write this down here, for any orbital maximum number of electrons is 2. Okay, so you can only put 2 electrons in an orbital. So the maximum number of electrons is 1 orbital times 2 electrons per orbital, so the maximum number of electrons is 2. Now, the p orbitals, I've already given the game away, it's more than 1 when I said p orbitals. There are actually 3 p orbitals, but each orbital still only has 2 electrons in it, but there are 3 orbitals. There are 2 electrons in each orbital, and so in the p orbitals we can have 6 electrons. So if you remember at GCSE, the second energy level we said had 8 electrons, and that's correct. But at A level we see that this 8 is made up of 2 electrons in the S subshell and 6 electrons in the P subshell. Okay, so that was fine. And now the D subshells, whatever energy level they're in, the D subshells, there are 5 D subshells. Okay, there are 5 orbitals in each D subshell. Okay, so if there are 5 orbitals, still we've only got 2 electrons per orbital. So that means the D subshells can hold 10 electrons. And just to complete, let's do the F. There are actually 7 F orbitals. And so if there are 7 F orbitals, still 2 electrons in each orbital, that means an F subshell can hold 14 electrons. And it's worth noting at this stage that we've included the F subshell here, so that you can know all the details of the first 4 shells, the first 4 energy levels. But actually in your exams you won't be asked to give the electron configuration of any atom that goes past the D subshell. Right, so you're going to stop at krypton. So there's no bigger atom than krypton that you're going to have to describe the electron configuration of, and there are no F subshells in krypton. Only when you get to period 4 do we get F subshells. Okay, and what I'd like to do also here is just to highlight the difference between GCSE and A level. At GCSE, remember, you had 2 electrons in the first, 8 electrons in the second shell, and 8 electrons in the third shell. and that was GCSE. All right, and that was because we stopped at calcium, and at calcium there are no D subshells. So these 10 electrons that you see in the third row, these 10 electrons weren't considered at GCSE, whereas at A level we do consider the transition metals and the D block elements, and so at A level we know that in reality there are 2 electrons in the first energy level, still 8 in the second energy level, but we've not only got the 8 from the S and the P subshells, but we've also got the 10 from the D subshell, and so we've got 10 electrons in the third subshell at A level. But I think it's probably worth doing that in a little bit more detail, so we might do that on the next slide. And here is that slide with a nice table for you. So in the table we have the shells, the principal quantum numbers from 1 through 4. And what we're going to do is we're going to list out the subshells in each of the shells, and then work out the total number of electrons that can be fitted into each shell. Okay, so let's start off right next to the nucleus in the first shell. So as we've mentioned before, we have just one, it's the first shell, and we have just one s orbital. And so there are 2 electrons in one orbital. So the maximum or the total number of electrons in the first energy level or shell is 2. Okay, we know that, that's the same as GCSE. And it's for the second shell. We now know that in the second shell there is an s orbital and there are p orbitals, right? And we know that there are 3 p orbitals. Okay, so we've got the 2 electrons from the 2s orbital or the 2s subshell, right? And we've also got 3 p orbitals and 2 electrons in each p orbital. So that's 8, and we're also familiar with 8 electrons being the maximum number that we can fit into the second shell. Okay, so let's move on to the third shell. So again, we have first subshell is the s subshell, and it's in the third energy level, so we call it the 3s orbital. And we also have next is the 3p orbitals, because we've got 3 p orbitals in the third shell. But now we've also got d orbitals. All right, so it's the third shell. We've got d orbitals, and you remember from the previous slide that there are 5 d orbitals. Okay, so let's count the number of electrons. First of all, in the 3s orbital, we have the 2 electrons. Then in the p orbitals, right, there are 3 p orbitals. That's in the third shell, so that will be 3 orbitals times 2, just as we had before. But now we also have the d orbitals, and there are 5 d orbitals, and each orbital has 2 electrons. So that gives you the total number of electrons in the third shell, and you can quickly work out that that is 18. Moving on to the fourth shell, we also have an s subshell in the fourth energy level, and in the same order we can say in the fourth energy level or shell we also have p orbitals, and there will be 3 of those p orbitals. We also in the fourth shell have d orbitals, and there'll be 5 of those d orbitals. And also in the fourth shell we're going to have f orbitals, and you might have heard me mention that there were 7 f orbitals. Okay, so let's just work through that again. I think I've got space if I do it nice and neatly. So we've got the 2 electrons in the 4s subshell, in the 4s orbital, and in the same way we have 3 4p orbitals, 2 electrons in each. We have 5 4d orbitals, 2 electrons in each, and now we have the 7 4f orbitals, 2 electrons in each. And so when we add those all up together, we can see that you can actually fit 32 electrons in the 4th shell. Hopefully that's been clear. Because you will actually have to remember these numbers for the exam. All right, so you will have to learn how many electrons each shell and subshell can hold. So now we're going to learn how to write electron configurations. And there are actually 3 main ways that we're going to learn. And why don't we learn it with an example? All right, so from your periodic table, you could pick out neon, and the information for neon has been highlighted there. And you see that the atomic number for neon is 10, which means that it's got 10 protons and it's an atom, so it's also got 10 electrons. So we're going to write out the electron configuration for neon, and we've got to write out, we're going to give the detail of the configuration of those 10 electrons. So the first way that we can write electron configurations is called subshell notation, and this is what it is. I'll draw it out for neon for you. So you just go through from the nucleus outwards. So in the first shell you've got an s orbital, and in that s orbital you've got 2 electrons. So that's 2 of the 10 accounted for. All right, so but we can't fit any more in the first energy level, so we move on to the second energy level, and the first sublevel is the s sublevel again, just 1 orbital in the s sublevel, so we're just going to put 2 electrons in the 2s sublevel or orbital. Okay, and also in the second energy level though, we do have p orbitals. And you'll remember that there are 3 p orbitals, and you can fit 2 electrons in each orbital, so you can fit 6 electrons in the 3 p orbitals. So we write it like that. So now you can count up, let me just change color to red, so you can count up that we have 2 plus 2 is 4, plus 6 is 10. So now we have accounted for all 10 of neon's electrons. So now what we have written here, I'll just underline it for you. Now what we have written here is the subshell notation for neon. Okay, so sticking with neon, let's write out that electron configuration in another way, right? And this way is called the arrows in boxes way. Okay, and the boxes that we're referring to, they actually are representing orbitals. Okay, so in the 1s orbital, right, let's draw a box like this for the 1s orbital. We have, of course, 2 electrons, don't we? And we draw the electrons as arrows, and the left-hand arrow points up, and the right-hand arrow for the second electron points down. And the reason why we have 1 electron pointing up and 1 electron pointing down is that for 2 electrons to occupy an orbital, they need to be of opposite spin. They need to be of opposite spin, and we represent spin by the direction of the arrow. All right, so to represent the fact that we've got 2 electrons in the orbital, we have 2 arrows in the boxes, and we draw the arrows 1 up, 1 down to remind us that they are of opposite spin if they're in the same orbital. Okay, so we also move on now to the second s orbital. All right, and you remember there's only 1 of those because it's an s orbital. So we draw 1 box, and again we're going to draw 1 arrow that's up and 1 arrow that's down. So that is the 2s electrons accounted for there. But in the 2p orbitals, I'm going to draw them along a little bit, right, because there are actually 3 2p orbitals. So I'm going to draw 3 boxes like that. And they're all full. Okay, so in fact, let's do it in order of them being filled up. All right, so that electron would come in first, then another electron would come into a new orbital, and another electron would come into the third 3p orbital. And when we got the three individual electrons in the 3 separate p orbitals, the next electron that's coming into that atom would come into the first p orbital, and you're going to draw it down because it has to be as opposite spin, and then the next electron would come in to the other p orbital, and finally the 10th electron would come into the third p orbital. So now, if you count all the arrows, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we have accounted for the 10 electrons of a neon atom, and that's how you draw neon in the arrows in boxes method. But as I mentioned to you, there is a third method, and this method is called the energy level method. So we draw a diagram of the energy levels. So to represent energy, I'm going to change to red, and hopefully I can draw a straight line. Okay, so I'm going to draw a line of increasing energy level like that. So then what I'm going to do, I'm going to switch back to black, and at the lowest energy level I'm going to draw a horizontal line like that, because that is the energy level of the 1s orbital. And I'm going to draw my box, my orbital box, and I have my 2 electrons in there like that. So that is the 1s orbital, and it's the lowest energy level, so I've drawn it down at the bottom there. Now adjacent to that, I'm going to draw the 2s orbital. Now the 2s orbital is of a higher energy level than the 1s orbital, so I'm going to draw it a bit higher up. I'm going to call that the 2s orbital. It's also just consisting of 1 orbital, and the 1 orbital has 2 electrons in it, so I draw them as opposing arrows just in the same way. Now the 2p orbitals, the 3 2p orbitals, I'm going to draw them on a horizontal line here. So these are the 2p orbitals. They're of a higher energy level slightly than the 2s orbitals, but I've drawn them above the 2s orbitals and not further to the right because they're still in the second energy level, or the second shell. So I'm going to draw my 3 boxes here, and then I'm going to put my electrons in those boxes. Well, a bit scrunched up, I'm afraid, but you get the idea. Okay, and so now what we've done is we've accounted for all 10 of neon's electrons in the energy level diagram, whereby the 1s orbital was the lowest energy level, slightly higher is the 2s orbital, and the 3 2p orbitals are of a higher still energy level. So that's how we do that. But just for completeness, I'll label my axis because this was energy, wasn't it? So here's a nice rule for you when you're working out electron configurations, and it is that electrons fill up the lowest energy sublevels first. So it's key to just appreciate this word here in the title, the lowest energy sublevels, and it will become clear why in just a minute. Okay, so to illustrate this rule, let's have a look at an energy level diagram. Here we are. We have, in the same way, we've got energy increasing as we rise up the page, and each of these, just going to rub out that underlining, each of these black horizontal lines represents a sublevel, and the lowest sublevel is going to be the 1s sublevel. It's also a level because it's the only sublevel in the first energy level. So we've got a 1s sublevel and as we've seen before, we have one orbital and we can fill it up with 2 electrons. So as we're going along, why don't we work out the electron configuration of, let's say, calcium. Okay, so calcium has 20 electrons, you'll see from the periodic table. All right, so atomic number is 20 electrons. So let's work out how to fill in the 20 electrons that calcium has. So the first 2 electrons are going to go into the lowest sublevel, which is this one we've filled in already. The next lowest energy sublevel is going to be the 2s sublevel. And again, that has one orbital into which we can place 2 electrons. So now we've accounted for 4 of the electrons of the 20. And so the next lowest energy sublevel is going to be in the second energy level, but it's going to be the p orbitals. And you'll remember that we have 3 p orbitals. Okay, so we can fit 6 electrons into, let me just draw it in this order just to be totally correct. Okay, so we've fitted another 6 electrons into those 3 2p orbitals. So now any new electrons that we have to fit in as we move along the periodic table, we have to go into the next lowest energy sublevel, which of course is going to be in the 3rd shell. All right, so and the lowest sublevel in the 3rd shell is going to be the s orbital, and we've got 1 orbital in that sublevel, and into which we can put 2 electrons. So there's another 2 of our electrons accounted for. Let's just check. We've got 2, 4, 6, 8, 10, 12. We've accounted for 12 electrons so far, and that 3s orbital is now full, so the next electrons are going into new orbitals. The new orbitals are going to be in the next lowest energy sublevel, which will be the 3p sublevel. P sublevel has 3 orbitals, just as the 2p sublevel has 3 orbitals. All p sublevels have 3 orbitals. Okay, so let's just count up 2, 4, 6, 8, 10, 12, 14, 16, 18. 18 electrons we've accounted for, and of course we've got to account for 20. Right, so we're going to next have to put the next 2 electrons into the next lowest energy sublevel. And I'm going to switch colour so you can see that this sublevel here is a lower, see, that's a lower energy, right, than the 3d orbitals. So these are the 3d, these are the 4s, right, and you can see that the 4s is actually a lower energy than the 3d. And so according to this rule, which is what happens in practice, then the 4s sublevel is going to be filled first. Even though it's in the 4th shell and we've not filled the 3rd shell, the next electrons, the 19 and 20 electrons, are going to go into the orbital that is in the 4s orbital. And so that is your electron configuration of calcium. So it did not go into the 2 electrons, 19 and 20, did not go into the 3d, because the 3d orbitals are of a higher energy level than the 4s orbitals. So the 4s orbital, rather, is filled first. There you have it. So what you would get, let's say the next element along in the periodic table is scandium. All right, is scandium, and that has atomic number 21. All right, so I'm going to pause for a second for you to work out where the 21st electron is going to go. Okay, so hopefully what you've spotted is that the 4s orbital is now full, 4s sublevel is now full, And so the 21st electron, scandium's new electron, all right, is going to go into the next lowest energy sublevel, which is in fact in the 3d orbitals. So we've got three 3d orbitals, and we're going to put the first electron in the first orbital like that. So that would be for scandium, that last one. Okay, here we have our second little rule to help us work out electron configurations, and that is that electrons fill orbitals in a subshell singularly before they start sharing. And this is sometimes known as the London bus rule. So imagine yourself walking up the stairs in a double-decker bus onto the top level, and you're looking for a place to sit. You're on your own, you don't know anybody who's up there in the bus, and you scan the seats. Now the seats are in pairs, aren't they? You got one bench with two seats on it in a London bus, and that's like an orbital, because in an orbital, of course, you've got two electrons, just like a bench in the upper deck of a London bus. Okay, so you're scanning these benches, and you go along there and you find an unoccupied bench, right? And you go and sit on that unoccupied bench, and so you're now on the two-seat bench on your own, just like everybody else is on a two-person bench on their own. And so then the next person comes up and will do the same. They will find an unoccupied bench with two seats and occupy that until all of the benches, all of the two-seat benches on the upper floor are full, and so the next person who comes up is going to have to take a bench which already has a person sitting on it, so then they pair up. But as you notice in London buses, people always sit on their own before they go and sit next to somebody else. That's why we've got this rule here called the London bus rule. Okay, so let's illustrate it with a couple of more real examples. Let's take nitrogen, for example, and nitrogen. Now, let's take nitrogen, and nitrogen's atomic number is 7, so it's got 7 protons, 7 electrons. Okay, and so we'll draw our orbital boxes. That's our 1s. Okay, so we've got our 1s electron with orbital, we've got our 2s orbital, and we've got our 3 2p orbitals, like that. Okay, and so we've got to fit 7 electrons in here, and the first 2 electrons are going to go into the lowest energy sublevel as per the previous rule, and the next 2 electrons are going to do the same. All right, but the 5th electron is going to go into the first 2p orbital. Now, so we've still got 2 electrons to account for, electron 6 and electron 7. Okay, so we have a choice now. We could write the 6th electron in the same orbital as the 5th electron has gone into, but that wouldn't be following this rule, would it? So the rule says the electrons are going to fill orbitals in a subshell singularly. All right, so that means it's going to fill in, 6th electron is going to go into the unoccupied orbital, and so is the 7th. You're going to get the 7th electron occupying occupying this orbital singularly, rather than pair up with either the other 2p electrons. So that's nitrogen, but if we were to go on to oxygen, I'm just going to switch colours, right, so I don't have to redraw the whole thing. We've just gone along the periodic table one step, because now we've got 8 electrons to distribute, and the first 7 are going to be the same as nitrogen, but when we move to oxygen, we've got an extra electron to distribute. Where are we going to put that? Well, look, all of these orbitals are now occupied singularly, right? So there's no option for oxygen's new electron to occupy an orbital singularly itself, because it can't go up to the 3s orbital, because we need to fill up this this lowest energy sublevel first. And so oxygen's electron is going to have to pair up with the first electron in the first 2p orbital. Okay, so that's this that's the illustration of this rule using nitrogen and oxygen. We've got one more rule to cover before you know exactly how to work out electron configurations. That's on the next slide. And our last rule is this, and it sounds a bit more complicated than it is. When we do a couple of examples, you'll see how simple this really is. But anyway, let's read it out. So for the configuration of ions from the s and p blocks of the periodic table, we're going to add or remove electrons to or from the highest energy occupied subshell. Okay, so let's just pick that statement apart to make sure we understand it. Firstly, notice that we're talking about ions. So we're going to, this is a rule about electron configuration of ions only. Okay, because we're adding or removing electrons. And secondly, let's notice that we're just talking about some of the elements, not all of the elements. We're talking about the elements in the s and p blocks of the periodic table. And it occurs to me that you might not be familiar with the different blocks of the periodic table, so we'll cover that in a second. Now we're adding or removing electrons depending on whether we're dealing with metals or non-metals, and we're going to do that, add or remove, from the highest energy occupied subshell. Okay, so let's just make sure we understand what S and P blocks are. So I've got a little diagram of the periodic table here for you, and you see here in purple, so I just changed to purple, you see here in purple we've got this group here nicely. Whoops, not supposed to include any of those D block elements. So that block there, groups 1 and 2, that is the S block, and it's named like that because the outer electrons are in s orbitals. And I'll switch to light blue for the P block. And the P block includes group 3 up to group 7. Group 8 are on their own. And that is the P block. And guess why it's called the P block? It's because their outer electrons are in p orbitals. And so what we are not including in this rule is the D block elements, and I'll highlight the D block elements if I choose a different color again. So the D block elements are these ones here. That's the D block. And that's because their outer electrons are in the d orbitals. Right, and so they do something different. We'll cover that later on. Right, but for this rule, we're just talking about S block elements and P block elements. So let's configure some ions. Why don't we, I was going to switch back to purple. Why don't we take magnesium? Right, so this is a metal, so it's going to lose electrons. So if we look at the atom of magnesium and write out its electron configuration, obviously it's going to be 1s2, it's going to be 2s2. We've got to account for 12 electrons, so that's 4 accounted for already, and then it's going to be 2p6, so that's 8, that's 10, and its last 2 outer electrons are in the third shell, s orbital, and there are 2 of them, and you can see that 2 plus 2 plus 6 plus 2 equals 12. So that's our electron configuration of an atom of magnesium, and when it forms an ion, as we know, it loses 2 electrons. It's a metal, it loses 2 electrons. It's going to form a Mg2 plus ion. Just write that down here, Mg2 plus ion. So the electron configuration is going to be written out according to this rule. So we need to remove, for magnesium, we're going to remove electrons from the highest energy subshell, that is occupied as well. So our highest energy subshell that is occupied, which is this 3s subshell. So we're going to remove those electrons. So we're going to keep our 1s2 obviously, and our 2s2 and our 2p6, and these are the two electrons that we lose. They have gone and they're not there. So that is our electron configuration of an Mg2+ ion, 1s2, 2s2, 2p6. Good, so let's now do the same for a non-metal. Why don't we pick chlorine? Okay, so I'll do it in blue because it's sort of like the colour of that P block in the periodic table. So again, chlorine atom, we see has 17 electrons, and so we're going to write out 1s2, 2s2, 2p6. That's the second energy level filled, so we have to go to the third energy now. First sublevel is the S, and that's full with 2 electrons, and then we've got 17, and we've accounted for 2, 4, 10, 12 so far, and so we need another 5, and they of course are going to go into the P because it's a P block element, 3p5. So that's our electron configuration of chlorine atom, and you can see that, I'll just switch colour for a second, you can see, just to make a little check, in your third energy levels, you've got 2 electrons in the S sublevel and 5 electrons in the P orbitals, and that equals 7, and that's what you would expect because it's in group 7. Right, so it's still got 7 electrons in its outer shell, as you learnt in GCSE, but now of course you know that they're split between S and P orbitals. Okay, back to the job in hand. We need to get a electron configuration of a chlorine ion now. So as you know, they make Cl1- ions because they want to attract an electron. So now we're going to add an electron from the highest energy occupied subshell. Okay, so we're going to add an electron to, rather, the highest energy occupied subshell, which is the 3p subshell. Okay, so let's go through the process. 1s2, 2s2, these inner electrons not affected. 2p6, they're all oblivious of what's going on in the outer reaches of the atom. We've still got 3s2, and into the highest energy level occupied subshell, which is this 3p one that we're dealing with now, we're going to add that 1 electron, so that becomes 3p6. So now it has 18 electrons, 8, 14, 16, 18 electrons, as you'd expect, because the atom's got 17, it's got 1 extra 1, so it's got 18 electrons. It's still got 17 protons, giving it a 1- charge. That's a chloride ion. So just lastly on electron configurations, or the way that we write them at least, let me tell you that sometimes you will see that there's a shortened way of writing electron configurations using the noble gas configurations. So here we have a periodic table again, and the noble gases all have their full p orbitals. And by the way, on the previous slide I said that P block doesn't include the noble gases. Sometimes you will see it including the noble gases, just so you're not confused about that. But back to these shortened electron configurations. Let's say we were working out the electron configuration of calcium, and as we know, the calcium it's got 20 electrons, so it's 1s2, 2s2, 2p6, 3s2, 3p6, and it's got 4s2 electrons, and there it's 2 outer electrons. Okay, so that's calcium, and that's quite a long. Once you get to bigger atoms, especially in the 4th period, that's it gets quite long-winded to write the whole thing out, especially as the inner electrons are always the same. So what we can do is we can write calcium like this as well. We can write calcium. So you see here's calcium in the fourth period. So what you do is you take the noble gas that's in the third period or the previous period to the element you're dealing with. So if you're, for example, if you were writing out sodium, for example, you would use neon as your noble gas. But for calcium, the noble gas that we've used is argon. All right, so you put argon in square brackets because the electron configuration of argon is so look, we've got 18 electrons, so we've got 1s2, 2s2, 2p6, 3s2 and 3p6 because its p subshell is full. So that's the same as the first bit there of calcium, and so you can write argon in square brackets instead of writing out 1s2, 2s2, 2p6, 3s2, 3p6. Just saves you a bit of time. And then you just finish off with the bit that changes, which is the outer electrons. So you write the 4s2 there for calcium. So they're alternatives. This would be the shortened version of the electron configuration using noble gases. Okay, so you'll remember a couple of slides ago we specifically excluded the transition metals or the D block elements from our third rule of writing out electron configurations. And so let's deal with those D block elements now. And I've got a periodic table for us to start with. Okay, so before we get onto the electron configurations of the D block elements, let's do potassium. All right, so I will write out the electron configuration of potassium like this. So we're going to use the shortened version. So we're going to start with argon, and as well as argon we have a 4, it's in period 4, S, 1 electron, it's got 1 electron in its outer shell, 4s1, and calcium is going to be argon again, all those electrons that are the same as argons, and then, but it has 2 electrons in its 4s shell, so calcium is argon 4s2. Now I'll just switch colour now that we're moving on to the D block elements. For scandium, okay, we're now having to go back to the 3D orbitals that weren't filled in. Remember, we skipped straight from 3p to 3d, from 3p to 4s, because 4s is the next lowest energy level, and the 3d orbitals, even though they're in the third shell, are of a higher energy than the 4s orbitals, so they are not filled when you're doing potassium and calcium. But now that the 4s orbital is full, we have to go back to the 3d orbitals. Okay, so the electron configuration of scandium is let's also have argon, right, for scandium, and we've got 4s2 and 4s2, and now we have to fill in those 3d orbitals, so it's going to be 3d1, just like that. And you could write it alternately. Notice I've put the 4s2 followed by the 3d1, so this is written out in the order that the electrons are filled in as you go along the periodic table, or you could write it down in order of energy levels, primary energy levels. So you could write argon 3d1 4s2, and you'll see both, and both are valid. So titanium, just for the sake of completeness, titanium is going to be argon, 4s2 is already filled in, and then you're going to have 3d2. Okay, and vanadium is going to be 3d3, etc. So chromium, I'm switching colour to red because chromium is the first odd one, and you need to be aware of this. Alright, so chromium is the first odd one. So let's do chromium up here. Of course, we still have all the same up to argon. And of course, we still have our 4s2 electrons. And what you would expect is, you would expect 3d, and it's 4 electrons, 4 elements on 1, 2, 3, 4. So you would expect 4 electrons in that in the 3d orbitals, 2 in the first and 2 in the second. That's sort of what you'd expect if you're following the same pattern. But this doesn't happen. This doesn't happen like that for chromium. All right, so I'm going to draw a little cross through that, and then go back to my red pen and write out what does happen. Okay, so of course we still have argon, and what happens is that one of those 4s electrons changes from being in a 4s orbital to a 3d orbital. So notice, of course, you've still got the same number of electrons in the s orbital and the d orbitals. We've got 6 electrons that we're dealing with, but why it does this is that you'll remember that we have 5 d orbitals, and now what chromium wants to do is it wants to have 1 electron in each of the orbitals. 1 electron in each d orbital. That is marginally more stable than having 4 out of 5 electrons in the 5 d orbitals and a full s orbital. All right, so it's actually got 1 electron in all of those actually 6 orbitals. One's an s orbital and 5 d orbitals. So now no electrons have to pair up, and so you don't get that repulsion between electrons that you do get when you have a pair of electrons in the same orbital. So that's why chromium is odd, and there's often a question on that. And I'll go back to blue because manganese is normal. And just to prove that, I'll do manganese, which is argon plus your 4s2 plus your 3d5. Sorry, I forgot my 2 there. Okay, so manganese is following the same pattern. So I'm going to jump, and then iron and cobalt would follow the same pattern as would nickel, but copper, I'll switch to red again because copper is also odd. Copper is also odd. So let's draw out in the same way as we did for chromium. Let's draw out what we'd expect. So you'd expect the argon, of course, followed by your 4s2 that were filled first, going back to 3d, and we need 9 electrons in the 3d because look, this is 5, 6, 7, 8, 9 elements along the d block. So you'd expect 9 electrons to be in your d orbitals. But that's not what happens. No, so let's draw a big black cross through that. That's not what happens. It's what you'd sort of expect would happen if you followed the same rules, but no, it doesn't, and it does make sense what does happen. So let's write out what does happen. Okay, so we've still got argon electron configuration, and what does happen is one of these 4s electrons jumps out again. All right, so you only got 1 left there, and gives you 3d10. So now what you have is you have a full set of 5d orbitals, and that's more stable than having your s orbital full and being 1 short of filling your d orbitals. So copper prefers to have all its d orbitals full and leave 1 short in the 4s orbital. That's what it prefers, and that's what it does. And then of course the d orbitals are remain full for zinc, and the 4s orbital gets filled up to 4s2 for zinc. So here's a little question that I'll pose you, and if you come to me with the answer in class, it would be interesting. So if going back to copper, a little question I put in green, if copper has a full shell of a full set of 5 orbitals, 5d orbitals, and only one electron in its 4s orbital, why isn't it really reactive? So that's the question. Why is copper not really reactive? All right, because you look back at potassium. Okay, potassium is really reactive, we know, and the only difference between copper and potassium is that copper has actually got a full 3D, full 5 3D orbitals, full 3D subshell, and one spare electron in its 4s orbital. So why isn't copper not really reactive? There's a question for you. Okay, and the last thing for this slide is about the ions. So it's the D block ions. All right, the last little unusual thing about the D block. So what you would expect is that the electrons that you would lose, they're metals, so they're going to lose electrons when they form ions. The electrons that they lose when they form ions would be the ones that went in last, those in the highest energy level. That's what you'd expect, isn't it? So if we take an example, let's take an easier example. Let's take scandium as an example. So I'll just draw a square around scandium. Okay, the electron that went in last was our 3d1 electron, this electron here. So when it forms an ion, all right, when it loses an electron, loses its first electron to form an ion, that's the electron you'd expect it to lose, isn't it? It's the electron in the highest energy level. But it doesn't. Okay, it doesn't, and nor do the other D block elements when they form ions. The first electron that they lose actually comes from the 4s shell. Okay, so loses these electrons when forming ions. Okay, so it's unusual, and the way that you can think about it, if you like, is that when you're filling electrons as you go along the periodic table, you're filling them in energy level order, but for the transition metals, when you lose electrons, you lose them in order of distance from the nucleus. So the 4s orbitals, you can imagine that they're further from the nucleus than the 3d orbitals, even though they're at a lower energy level than the 3d orbitals. Okay, so I'm just going to write out this little rule for you so that we make it clear. So when ions are formed, it is the 4s electrons that are lost first. Not quite what you'd expect, but there it is. Okay, so that concludes the video lesson on electronic structure. It seemed like quite a lot for 2 little lesson objectives, but there was quite a lot in these 2 lesson objectives, especially the first one. So hopefully now you're able to write out electron configurations of all the atoms and ions up to atomic number 36. And you're also aware that for transition metals, the order of filling electrons is different from the order of loss of electrons. So they lose the 4s electrons before the 3d electrons. So in contrast to previous video lessons, I wonder if what you would do now is complete a little survey on the next slide, whereby you let me know whether you've got this content or not, so that if not, I can cover it again in class. Anyway, thank you very much for listening, and I'll see you in the next video lesson.